going to do it with F#, and we're going to do it with Rubik's Cubes. So this talk's going to be a little bit different. For example, I'm going to have this guy over here scramble this for a few minutes while I get this started. So point one, I hate PowerPoint, but I do like Markdown. So I have these little Markdown bits here with my whole talk, and I'm going to use F# to compile this down to slides. So I'm going to run this little script here, this build script, and it's going to go and grab some packets, basically like NuGet packages. It's going to download some JavaScript libraries. I'm going to do a whole bunch of magic, and eventually I'm going to have slides. And if this doesn't work, I have a backup, so we're good. So it's not going to like fail on me if the internet's a little bit sketchy. So yeah, it's going to do some downloads here, and then we'll get started with some slides. And this talk is going to be mostly slides, if not entirely slides. And that might make you sad, but there'll be a lot of code on the slides, so I think that counts. All right, should be about done here. Yay, it worked. Cool. So first thing, just to show my credibility as someone who does the Rubik's Cube, I've been doing this for about 8 years, on and off. I've gone to competitions. I went to nationals last weekend to help sell some Rubik's Cubes. So this is a big part of my life, and it has been for a while. I'm pretty slow. You might be thinking that I'm kind of fast, but you're wrong. I'm really slow compared to some people. So there you go. So credibility served. I can solve Rubik's Cube. So during this session, we're going to make a Rubik's Cube solver. It's going to be really bad, right? It's going to do it really slowly, because that's harder to do on a computer than it is with your hands, believe it or not, until you know what you're doing. So throughout this session, we're going to build a really bad Rubik's Cube solver. I'm going to show you a lot of F#. So who am I? My name is Stachu. I solve Rubik's Cube sometimes. Sometimes I quit for 6 months because I'm too slow, and sometimes I'm back into it, whatever. I work at Academy 1 in Malvern, Pennsylvania, so I flew down for this. They make me write C#, which isn't F#, so it's not as cool, but hey, I don't have to write VB, so I like them for that. I like weird tech. I like F#, Haskell, Lisp, Scala. Scala not as much, but all the other languages great. I like weird databases like Neo4j, RavenDB. I like meta-programming, machine learning. Basically, that's my, I like walks on Code at the Beach. I'm just kidding. And that's what I'm about. So some goals of today, I'm going to introduce you to the Rubik's Cube. So it's not quite a tech talk, although it is in some regards. I'm going to kind of sell you guys F# and maybe some property-based testing. We might go into that. I want to represent a Rubik's Cube in F# and talk about group theory. So we're going to go into abstract algebra today, so that's going to be cool. We're going to turn the cube. We're going to scramble the cube. We're going to solve it really inefficiently, do a bunch of testing along the way, and I'll try to claim that F# is better for testing both C# code and F# code than C# is. And we're going to talk about how the program could be better if this was 2-hour or 3-hour long session. And again, we're going to have a lot of different tests along the way. So some important domain-specific knowledge. I assume everyone knows what a Rubik's Cube is. Otherwise, you probably wouldn't have shown up to this. So I'll assume that. So what makes up a Rubik's Cube? You know, what's composed of this? If I were to take this apart, which you can do, you know, what are the pieces looking like on the inside here? And this is going to be important when we actually create our solver. So the first point, that's kind of the core of the whole structure here, is the centers. There's 6 of these centers, the normal white, yellow, blue, red, green, orange, although I replaced my orange with black since I'm colorblind. And so this is like the core part of it. So there's 6 of these. And one important feature of this is that you can see from the picture here is that they never really change relative to each other. For example, the white is always going to be opposite of the yellow, the blue opposite of the green, and the orange opposite of the red. So that's important to keep in mind as we create our solver here. All right, so we also have edges. These things kind of in the middle of 2 centers here, which have 2 stickers. Because of the properties of these centers, there will never be an edge with a yellow and a white sticker. Just because they're on opposite sides of the cubes, it's not possible. And finally, we have corners. Corners for the guys at the corners here. They have 3 stickers, and likewise, they cannot have 2 stickers with opposite side colors. So how does this thing move, and how do people that do the Rubik's Cube talk about it and kind of represent the notation that's built in here? Well, since there are 6 sides to it, there are really 6 axes that we can turn on. really 3 axes, but 6 sides that we can turn on. We can turn the right side, which is literally, if you're just staring at a cube, I like holding yellow up and blue front. R is just turning the right side, L is turning the left side, U is turning up, D down, front, F front, and B back. And by default, each of these turns are clockwise. And so because of those 6 different axes we can turn on, there's 18 basic turns on a cube. And we'll see how that number 18 is going to cause us a lot of pain later when we get into exponentiation. For each of the turns, we have like the turn counterclockwise, and the turn 180 degrees. So that's like clockwise, counterclockwise, 180. You get the point. And 180 doesn't matter, the rotation, since it's under an 80. All right, so those are the basic moves of the Rubik's Cube. And an example algorithm would be this, the F, RU, R prime, U prime, F prime. And that, as a person who solves Rubik's Cube, that means something to me. Specifically, it means I'm going to do these moves. That might have been quick, but basically 6 moves representing that I'm going to turn the front face, the right face, the up face, right face counterclockwise, up face counterclockwise, and F face counterclockwise. So you don't have to like memorize all this notation. We'll go into a little bit later and see how we represent it in the in F# here. So last piece of domain-specific knowledge before we get into some code. At some points, we need to label some pieces by their location. For example, let's say I am holding a Rubik's Cube with the yellow face up and the blue face front. If I wanted to talk about this piece here, over here, I could say, oh, it's the yellow red sticker. But more appropriately, we're going to call it the upright cubicle. Cubicle being like the space it can take up. And we'll see how that'll make some sense. And of course, right here, I have a corner notation for, I have a notation for a corner, which is the upright front right here. So that is some domain-specific knowledge. Any questions before I go along? And feel free to, ask questions as we go. This is a pretty loose session.
Domain is a center never move.
A center will never move. I mean, you can rotate the cube, but they will never move relative to each other. And when you write a solver within any language, you usually just try to keep the cube stationary. You don't do any of those kind of rotations, just to simplify it. Yes?
On the label piece by location,
yes.
Is that based on what the current configuration is, or is that what from the original configuration?
Well, it's the original. So like if I have, like, let's say I messed this up, and the piece that's supposed to be over here is now over here, right, because the turns I just did. In that case, this may be the UL piece, because it was originally in the up left cubicle, but right now it is in the upright cubicle. So we can talk about a UR piece or a UR cubicle. And in the original configuration, the UR piece is going to be in the UR cubicle, but not necessarily once you mess it up. Any others? All right, cool. So how do humans solve this thing? You might have seen people on YouTube solve it fast. Just last weekend, some kids solved it in like 8 seconds on average. It was pretty fun to see. As a comparison, I solve it in like 15 seconds, so double the speed. So I'm just going to breeze through one method that is used once in a while called the roux method, just because it's a simple method to comprehend. But the general gist of any of these methods is pretty much you solve it like a jigsaw puzzle. You know how like you get the edges, and then you try to get a bunch of the blues, and you try to get the green grass, and then you try to push things together. That's kind of like that. You just kind of want to reduce the puzzle down to a simpler state. And if we have time to talk about some more complicated methods at the end, then we can talk about some computer efficient methods that will use some of those kind of properties. So in the roux method, the first step is we solve a 1 by 2 by 3 block. You can see those green pieces there. It's basically a little block. After that, we're going to solve another one on the other side. So we have 2 mirrored blocks here. And then we're going to solve the corners on the top here. And then finally, we can solve the rest. I know that might not make sense, but you can think of, just for reference, it's useful to know kind of how people do this. So now that we talked about Rubik's Cubes for a while, I guess we should talk about some tech, since we're at a tech conference. So what is F#? F# is a .NET language, kind of like VB or C# or I think you can even get Iron Python to work and access all your .NET libraries and your ints and your strings and whatnot. So it compiles down to IL, and you can use IL Spy to look at your code and all that stuff. It ships with Visual Studio. F# 4.0, I think the RTM just came out with 2015, although F# has actually been in your IDE since, I believe, 2010, if not earlier. So you've been downloading some F# source compilers for a while now, whether you knew it or not. Just for a feel, how many of you have actually played with F#? Cool. It's not at all a prerequisite for this talk, so don't feel like I'm going to go over anyone. So F# is a functional first language, and what that means is it treats functions as first-class citizens rather than objects. In an object-oriented language, kind of objects are the main construct, and we build our entire program around that. Whereas in F# or Haskell or any kind of functional language, we tend to think of things a little bit differently and think of functions more than objects here. Although it is functional first, it's very accepting of imperative and OOP paradigms. I don't think I do any OOP within this talk, but there's definitely some imperative code, such as for loops and that kind of stuff that we'll look at. It's statically typed, so where I might not explicitly state a bunch of types all the time, it is .NET code. It is statically typed. You're not going to have to live the pains of JavaScript on the server side. And it has a REPL, and we'll look at that a little bit later. And it's kind of like C#, but with less bugs and less code. That's how I like to think of it. I haven't seen a null reference exception in months for side project stuff. So compared that to C#, where I see that once in a while, it's good to not have it. So you might be asking a little bit more about, what is functional programming? Is it functions? Is it purity? Is it monads or category theory? Well, the answer is yes, kind of, for all these things. But for this talk, I don't care. Like I say, monads, mo problems, right? You might hear some Haskell people talking about monads, so that's a little. Yeah, but yeah, F# is really awesome, even without FP. So I try not to berate the code that we'll see in this talk with too much functional programming. And I have some imperative for loops and that kind of stuff, so you can get your feet wet while still looking at the general syntax of F#. But I won't dive into monads today or category theory, any of that. So one little selling point of F# I want to make is that complex things are a lot simpler in F# a lot of the time. Sometimes they're harder, but a lot of the time they're easier. For example, let's say I was modeling a Walmart or something. I don't know, some store in which I had workers, and I had, within the workers there are employers and employees, or managers and workers, sorry, is what I put here. If I want to make a simple type of just a person with a first and last name, it's pretty simple. I can just say type person equals, and I get this colon thing, and I can say that each of the first and last name are strings. And within one line, I declare that type. So that's pretty equivalent to declaring a class in C# with two different properties that are auto get set. Although this is immutable, but we don't have to talk about that. So within one line, I probably covered what we would have done in C# and 4, 5, 6, whatever. And next, I have an employee type. And an employee type can be either a worker or a manager. So if you're a worker, you're just a person. You're just a person that works there. You get paid, whatever. But if you're a manager, then you're a person, and you also have a list of employees that you're managing. And so this is what's called a discriminated union. And it's basically a way of kind of like enums of having one type that represents a number of different conditions. But it actually compiles down to a class hierarchy. So if I were to program something like this in C#, I'd probably have to have a base abstract employee class, a worker class deriving from that, and a manager class deriving from that. And they'd probably all be in different C# files. So I did in 3 lines of code what I would have done in 3 files of code in C#. So like I said, F# makes things a lot simpler. Not all the time. I mean, this is a pretty edge case. But it does absolutely do it. All right, so F# can do anything that C# can do. We have all kinds of classes and interfaces and inheritance. We can do link and things that are even cooler than your normal C# link. We have advanced reactive extensions, functions, XML comments, actually shorter XML comments. We can work with the web. I've written sites using MVC, Web API, NancyFX, all with F#. You can also use a bunch of different other web frameworks such as SignalR or Service Stack, and heck, you can even compile down to JavaScript using things like WebSharper and Pit and FunScript. And if you go online to the other guy that's speaking about F# during this exact time slot, there's a YouTube. Yeah, thank you for choosing me. there's a video of Ricardo giving a talk on doing SignalR for fast web. I highly recommend that. It's a great talk, and it talks all about compiling F# down to JavaScript and then utilizing some SignalR hubs to access data real time. So that's a very good talk to watch online. And finally, F# works with WinForms and ETO.NET and WPF, and also will work with this Xamarin. So you might not be able to see everything here, and that's kind of intentional. This is a project written in C# called SpecFlow. And there's nothing, I don't have anything wrong against SpecFlow, but this is the dependency diagram of SpecFlow, written in C#. A similar product called TickSpec is this. So a lot less dependencies, a lot cleaner. Again, the guy that found this probably found an edge case, but it still exacerbates a point that there's a lot of things are a lot simpler in F# some of the time. But anyway, I'll stop selling F# for a little bit, and I'll start actually showing you some more code. So the first thing we want to do is we want to represent this thing in F#, because it's just a great language. So before we do that, we're going to talk about group theory for like 2 minutes. So imagine the numbers 0 through 5 under addition modulo 6. And by modulo 6, I just mean like the mod function or the percent modulus function that we have, where like 15 mod 6 is going to be some number, I don't know. And basically, if we have 2 of these numbers here, let's say we're adding 1 and 2, and then we do a modulo of 6 to that, it's going to be 3. And if we do 4 and 5, that's going to make 9, and then we do 9 modulo 6, it makes 3. And this is going to be important when we talk about the cube, because the cube is actually a group under abstract algebra, and we don't have to go deep into math. That's fine. Yeah, I brought you to a functional programming talk, and then I added more math. But one important note to state here is that while we have all of these normal additions here with under modulo 6, there's one important case, 0, which is known as an identity. And basically, whenever you add 0 to something, it creates the same number, the same member in that group. And we'll have a similar identity that is the solved cube, and we'll see that in a minute. So now that I talked about group theory for a second, we can represent the entire Rubik's Cube in 4 interarrays. We can actually do it in a lot less, but for the sake of this talk, I'll do it in this slightly more verbose style. So this is what we saw before, kind of what's called a record type. It has these little not semicolons, but curly braces, and we have our colons inside. And basically what this is stating is that we're creating a type class which has 4 different members in it, as edge positions, which is an interarray, edge flips, corner positions, and corner twists. So what is a corner twist, and what is an edge flip? Well, if you give me a minute just to solve this, I can tell you. So a cube can be well, it wasn't very scrambled. So if edge positions and corner positions were already talked about, when I talked about the UR piece being in the UR cubicle, it's just the position is what cubicle a piece is currently in. But a twist or a flip is just stating the fact that while this piece may be in this slot, it could be twisted in one way or another way. So the corners have 0, 1, or 2 corresponding to each of the twist states. And the edges could also be flipped in place as such. Okay? So that's what we are storing in these arrays. And I may do some hand wavy stuff to try and define, how are we translating from one state to another in the cube. But that should be the only hand waving we do in this. All right, cool. So we are going to, now that we defined the state of a cube, we should define the state of a solved Rubik's Cube. More explicitly, the edge positions are going to be an array from 0 to 11. And this is a nice little syntax It's a shortcut for literally numbers 0 to 11, just 0, 1, 2, 3, etc. We can create arrays of 12 elements, all being zeros for edge flips, since when the cube is solved, it's not flipped at all. All the pieces should be correct. There are 8 corners, so we have the 0 through 7 there representing each of the positions of them, basically stating that corner 0 is in the slot of corner 0. That's what the 0 is meaning, and 1 is in 1, 2 is in 2, etc. And finally, the corner twists being an array of 8 length and all zeros, just stating that the pieces are in the correct state and they're also not twisted. So that is a solved Rubik's Cube. Any questions so far about the whole state thing? Cool. So later on, we're going to need to take those 18 different transformations I talked about before, the R and the R prime and the D and the D prime, and we're going to need to store that in a nice and easy way to A, relay to the cuber who wants to find a nice algorithm they're going to put in their solution and they're going to use this program for, and B, to use throughout our unit tests and all that stuff. And speaking of unit tests, hold up, buddy. Your test coverage is 0%. This is 2015. We love our test-driven development, I think. So we need to write some tests, right? It's pretty common these days. Now, I want to claim that writing tests is at least slightly better in F# than C#. And some of the times it's a lot better, but we won't see all that today. So there's a number of things to take from this slide. Number 1, open is the equivalent of using. Pretty simple. And cube is a namespace or a module that I created before. Attributes look pretty much the same. We just have an extra brackets. Another cool thing is we can actually name variables to be this with this double backtick. And what that helps us do is when we're running our unit tests in ReSharp or whatever we run them in, they don't have to be uppercase, lowercase, uppercase, lowercase, and all that jumble that it's impossible to read, and I spend half my time writing unit tests just trying to figure out a name for the unit tests. Instead, I can just write it as a string, and I can see that, oh, solved cube has 12 edges, passes or fails. Just like a human would read it, right? So that's nice. And the tests here are pretty simple. I'm just checking to make sure that the solved cube or any cube has 12 edges and 8 corners. So we have this little project called FSUnit, which is a wrapper around things like NUnit and XUnit and whatnot, in which case we get this nice little should equal syntax. And don't worry about these pipes. Basically all they're doing is saying apply the function on the right to the stuff on the left. But we won't see too much of that as we go. All right, so this is some code I found in some open source library on GitHub when I was using trying to create this cube solver and to create this presentation. And it's OK. I mean, it's like, I don't know, 20 lines of code or something. And it's kind of bulky. And it's using tuples, which are cool. But the tuple support in C# is kind of weak. So I did a little bit of work, maybe 10 minutes. And I simplified it, I think, a lot. It's still not amazing code, but it's a lot cleaner. You'll notice that before, we had these for loops running through all of the different pieces in the cube, and we had it converting a bunch of different things. But in F#, we use something much more like link in C#, where this is basically select, and we're projecting from the current pieces on the cube to a new set of pieces on the cube. So this is the hand-wavy stuff that I was talking about, just because of time constraints. The actual turning of Rubik's Cube is not super complicated, but there's no real way to visualize it without lot of visual work. But basically what this is going to do is this function is taking in 2 parameters that are both cube states. I mentioned before that each situation you can come across in a Rubik's Cube is part of the Rubik's Cube group, similar to the numbers 0 through 5 being part of that addition modulo 5 group. And so what you can do with that is similar to how you can add 2 numbers in any of that set. You can also multiply 2 different cube states onto each other, which sounds kind of crazy. But basically what it means is that when I want to later notate the fact that this R turn is is putting this piece here and this piece here, etc., I can store that in the exact same mechanism I can store the rotation in the exact same mechanism that the number 2 is stored in there. So it's a similar analog. And this function, all this function does, is it applies, basically does that multiplication from one cube state onto another cube state. And all this code is on fsolve.net. I have all these slides thoroughly documented there. So you can look at that later. I have a card you can take after if you want to look in this more deeply. So next test we want to write is very simple. We just want to make sure that my identity function is correct, that if I take a solved cube and then I take the transformation that is the solved cube, when I apply 0 plus 0, it basically returns 0. So this is pretty simple. We just take a solved cube, we apply the solved cube position onto it, and then that should equal a solved cube. And one cool thing about this, you might be thinking, how is that going to work with referential equality? What if they're 2 different objects at this point? One feature of F# is that we have structural equality by default. So if I have a list that is from 1 to 10, and I create another whole list that's from 1 to 10, it's not going to say, hey, those 2 references are different. It's going to say, yeah, the internal members of those are the same, so I'm going to treat them as the same. So that reduces a lot of headaches. I haven't had to write a get hash code function in a while, which is always a pain. And you can make it referential equality if you want. But anyway, so this is the hard work I did in trying to map out the turns and the twists and that kind of stuff on a Rubik's Cube. This is just the R turn. When I just do this, all those numbers happen. None of the edges are flipped according to what I mean as a flip, which I can hand wave about that. But a lot of positions are mapped around the cube. So don't worry about this too much. It's basically, all of this is basically like the number 2 in the other group. It's just a mapping from one set to another. And of course, we have similar definitions for the rest of the 6 basic turns. And we're going to need something besides the 6 basic turns. We're going to need, from R, I can define R prime as literally doing R 3 times. So I'm going to utilize that in my code. So what this function here is going to do is this is something called pattern matching, which is really cool. It allows me, it's basically like a switch case and an if statement, but not horrible. And it allows me to basically execute a cube state onto a cube a number of times. And you don't have to look at that code too much, but it's very nice. And another thing we want to do is the ability to combine a number of different states, and we'll go to that later when we get to that code. So basically, the first execution helper is the more useful one here. It's basically going to allow us to derive the other 12 moves from the 6 basic turns. So as I said, we're going to apply this execute n to solved cube with the move R 2 times or 3 times to derive the different twists. Pretty simple. And later on, we're going to need a move set in our program to allow us to actually utilize a solver and a scrambler. So we're going to create this static member here as part of this type. And this is pretty much like a static class, the type above. Actually, that's not true. It's just a class with a static member. So more tests. Actually, before I get to these tests, any questions? I know I hand waved over the application of a cube onto a cube, which seems very abstract. But the point is that mathematical aspect of this talk isn't that important. Are there any questions elsewise? Cool. So more tests. I want to have a little bit more fun with structural equality. If I apply the move R to a solved cube, it should not equal a solved cube. And this is another nice feature of FS unit. This unit test is very illegible, I think. I take a solved cube, I execute something onto it, and it should not equal a solved cube. That's very legible. So thank you, FS unit. And again, we have the nice naming convention. Just giving a solved cube, R should mess the cube up. And it'll check all the internals, all those interarrays at runtime of this test. And it'll make sure that the internals are not the same, rather than just checking the reference. So some more tests. There are some useful properties to know about the cube that, when I'm creating the solver, I want to test to make sure that my turning mechanism is working correctly. One of them being that if I make if I take any of the turns, any of the 18 basic turns, and I do it 4 times, I should end up in a state where it's not messed up. So I have a little test here, move to try, and then it iterates through those, and for each of them, it'll execute it 4 times, and then make sure it enters a solved cube. Another thing is I'm going to use that combine method that I created earlier, and I'm going to create a variable called a tperm, and the naming convention's weird, but basically these moves are all stored right here. I think it's like 14 moves long, and what that does is it flips it exchanges these 2 pieces and these 2 pieces, and by that property, if I do it twice, the cube will be solved. So one thing I want to test is A, to make sure that combine function works, and B, that if I do that series of moves twice, I end up in a solved state. So just checking some properties, testing is very nice, and it helps me verify everything we got here going on. So the next step is to create a scrambler. This is a really bad scrambler. It's actually incorrect according to like the standards of the people that make Rubik's Cube scramblers for like official competitions. But for this session, it's fine. Basically, what I'm going to do is I'm going to take in a cube state, probably a solved cube that I'm going to scramble, and I'm going to pass in a list of moves that I'm going to allow to scramble it. And from that, I'm going to create a randomizer. I'm going to create a scrambled cube. And again, this is going to be mutable rather than all the other bindings which have been immutable. And I'm going to store the number of moves performed. And basically, from 1 to probably 25 moves deep, I'm going to scramble the cube. And there's a lot of syntax going on here. But basically, this is our assignment operator. They purposely make it ugly so you don't do assignments because assignments are bad in F#. And if you want to combine lists, we have this Haskell-like thing here where we're appending ahead. Where we're taking 2 lists and we're appending them together. But one cool thing to note about this function is that in F#, the last part of a function is always the thing that's going to be returned. So rather than in C# where I have a return anywhere I want in the body, escaping the function as we call it, kind of like goto. Instead, we have just one return at the end. And in this case, I'm returning a tuple, which 1 is a cube state and 2 is the list of moves in that notation that we saw earlier, and the RU, R prime, U prime, et cetera. So very basic scrambler, and I want to make sure that it works, of course. So I'm just going to take the scrambler, and I am going to give it a solved cube. I'm going to apply 25 random moves out of that set of 18 moves. I'm going to do it 25 times. I just want to make sure that it's not solved. There's a chance that it could be solved. I mean, if the scrambler just went like this back and forth randomly, then it could be solved, but very unlikely. So this test will mostly pass. All right, so we should actually solve the cube, right? You've been in this talk for a whole while. I've claimed that at the end of this talk we're going to solve a cube, so we should actually do it. So what we're going to do is we're going to make a basic tree search. And a basic tree search is something that takes in 2 parameters. 1, the set of allowed moves, probably those 18 basic moves that we defined earlier, and the number of layers deep to look. And here's some code that does that. I'm sorry about the thing being cut off, but on my screen it works. Basically what this is you can gloss over the code or look at it as I'm talking. But what it's basically going to do is for each of the 18 moves, for each layer deep, it's going to branch out. So like if I just told it to scramble with the whole 18 moves at 1 depth, it's going to go through each possibility of spidering out and doing each of the 1 move, each of the 18 moves. And if that's not true, or if none of those cases are solved, then you don't have a correct solution. Then so again, if I pass in like 3, and I say I want to go 3 deep, then it's for each of those 18 things it spiders out to, each of those possibilities, it's going to spider out again. So we're going to get 18 to the 3rd possibilities that we're going to iterate through. But that's horrible, right? Like it's really bad. So this is how good I am at paint. This is an exponentiation of my badness of paint over time. At age 2, I was this much bad. No, I'm just kidding. But this is just with like as if there were like just 2 moves possible in the cube, but there are 18. So you can imagine, this is just 2 to the 5th here, 32. But if I did 18 to the 5th, it'd be huge. For example, if I do 2 deep of 18, 18 to the 2, I get 324 possibilities. If I search 9 deep, I get like 198, what is that, billion or something, or trillion? I don't know, billion. So that's really bad, right? Because like computers are fast, but they're not that fast. And cubes can be scrambled up to 20 moves deep. So like no matter how many turns you do it, it can always be solvable in 20 moves. That was proved, I think, 2010. You can go to cube20.org if you want to check the proof out. But basically, you can imagine that 198 billion number, and if you like square that and then you add some more numbers and sprinkle them on top, that's about how many solutions, or that's how many iterations we'd have to go through, which is really bad. But we have things that can help us, right? So like our solution that we just created, the basic tree search, is it's pretty okay, but what if a cube is scrambled 3 moves deep and I only tell it to search 2 moves deep? At that point, it's just going to say, oh, I give up. No solution was found. What we can do is we can instead say, I want to search all the possibilities of 1 move deep, and then I want to search all the possibilities of 2 move deep, and then 3 move deep, and et cetera, until I find a working solution, rather than the computer just bailing on us. So is it going to help us? Is this going to rescue us? Not really, but it'll help us a little bit. Not much, though. So again, we have a function called IDA search, and IDA just stands for iterative deepening algorithm, I think. And basically, given a max depth, let's say 10 in this case, and a scrambled cube and probably a solved cube, and a number of allowed moves, we are going to call the tree search internally, and we're going to iterate upwards and say, okay, call the tree search for level 1 deep, then level 2 deep, and level 3 deep, et cetera, until we get some solution. Hopefully, the max depth is large enough that we can actually get a solution. So this helps us in one aspect, that we can eventually get a solution if we plug in a large enough max depth, and the basic tree search won't just quit on us. But we're still going to have to go through all those iterations that we mentioned before. It doesn't help this. But nonetheless, although it's really bad, we should test it because red-green refactor, right? So red-green, we technically have a working solution. So what I'm going to do here is I'm going to create a test that is just testing the fact that a scrambled cube should be solvable. So I'm going to say the depth I'm going to scramble my cube and the depth I'm going to look at is going to be 3. So the first thing I'm going to do is I'm going to create a scrambled cube, and I am going to basically take that scrambled cube and plug it into the IDA search, which is thus going to call the basic tree search internally. And I'll get 1 second, that'll get you. And basically what we're going to do is we're going to call that search algorithm, and we're going to say, okay, go exponentiate, just deal with the pain of trying to find a solution. And if you find one that's, if you find at least one solution here, then pass the test. Yes?
So at a depth of 3, is that to say that you took a solved cube and made 3 moves?
Yes. Yeah, the scrambler is just allowed to make up to 3 moves. Any other questions at this point? Cool. So we have a test, and we have a technical scrambler. So I fulfilled my duty of creating a scrambler within this talk, but it's really bad. And if we plugged in an actually scrambled cube, which I think the average scrambled cube is taking about 16 moves deep to solve, then it could take years or thousands of years for my solver to actually work. But there are ways of doing this more efficiently. So we have 2 options at this point. One, I can talk about ways to make our solver better. Time kind of warps when you're speaking, so it's going a slight bit faster than that was anticipating. So I can either talk about these different methods and how we can make your solver better, or I can show you some more F# and how F# is better than C#. So general consensus, which one? Okay, raise your hand if you want to hear me talk about Rubik's Cube some more, or yeah, that's the first option. All right, you got like two, yeah, a few. Okay, let me know if you want to hear about F# some more. All right, so it's F# time. Cool. All right, so I did a demo a few weeks ago at Philly.net, which is near Philly. It's in Malvern, actually. And basically, we did this thing called lightning talk. And what that is it's about 15 minutes worth of talking about something. And luckily, we actually have about 15 minutes left, and I have the whole demo right here. So let's do this. So one thing that's really cool about F# is pattern matching. Can anyone not see this? OK. I'll do some zooming magic. Can anyone not see this now? So if you can't, you probably have problems. So does anyone not know what FizzBuzz is? FizzBuzz is a pretty common problem. Basically, input a number from 1 to infinity. And if it's divisible by 3, output fizz. If it's divisible by 5, output buzz. If it is divisible by both, then output FizzBuzz. If it's not divisible by any of those things, just output the number. In F#, we have pattern matching. And I showed you a little bit of pattern matching earlier, but here's some more. Basically, this FizzBuzz1 function takes an int, and it returns a string. And you can see here, I'm not specifying any types. I just kind of magically get all the types going. And the compiler even knows that this is an int. And basically, what I'm going to do is I'm going to do a pattern match on I mod 3 and I mod 5 with this body of different cases. Kind of like a switch statement, kind of, not really, better. But and basically, if I mod 3 is 0 and I mod 5 is 0, then I'm going to print out FizzBuzz, and sprintf is basically like a string format in C#. You're probably used to. If it's only visible evenly by 3, then print out fizz. Otherwise buzz. Otherwise just print out the string itself. So that's pretty nice. And if we take this code and if I run it, which I can do by highlighting code then saying execute and interactive, then I can have this little window pop here, and it will execute the code for me without me having to compile or do any of that kind of stuff. I can just say, I want to see the code now. I don't want to wait for me to hit Control-Shift-B and then F5 or what any of those things. I just say run it now for a lot of the time. So right now, we can see the results. You might not be able to see it, but I can't zoom in on this without some work. So as you can see, number 1 goes to 1, number 2 goes to 2, 3 goes to fizz, et cetera. So we have a working solution of FizzBuzz. And that's pretty nice. So besides that normal pattern matching, there's this thing called active patterns, which are like pattern matching, which is already better than if statements and switch statements, but then even better than that. So I can abstract away different logic that I need to use within a pattern match with something called an active pattern. And what I'm going to do here is I'm going to create an active pattern called fizz and an active pattern called buzz. And all this is going to do is this is going to return an option type, kind of like a nullable type in C#. And given these two active patterns, which we'll slightly gloss over, I can create a pattern match which is very, very legible. And I can show like a BA to this, because the BAs need FizzBuzz all the time. And and I can explain to them like, hey, this is our problem. This has seemed like a correct implementation. If something is fizzy and buzzy, then should I print out FizzBuzz? And they'll be like, yeah, of course. Except for the edge case when you don't, because the client didn't tell us about that. But anyway, if I take this and I create FizzBuzz2 given these two functions, then I can take this iteration of FizzBuzz2 and I can print it out. So I get the same exact implementation I had before. So that was pretty cool. Any questions about active patterns or pattern matching? Because there is a lot to learn about it. There's one guy that gave a talk just about active patterns. So not here, but at some like F# thing. Anyway, so pattern matching is really cool. Another thing that's really cool is structural equality. So if I create a type called person, like I did somewhere within the slide deck, and the person just has a first name and last name, both being strings, then if I create two people independently, with different references or whatever, called person1 and person2, and they have the same exact internals, and apparently their first name is both lowercase, I don't know why, then if I check to see whether the two John Does are equivalent, it will return what we'd expect as a human being rather than as a software developer thinking of referential equality. So right here, if I highlight all this code here to create my types and to create my two people, and then if I evaluate whether the persons are equal to each other, then it will return true. And if you want to feel pain, and if you want to deal with referential equality, no worries, we have that. All you have to do is put on this attribute called reference equality, very good naming convention, and then when we do our equality comparison, it will be false. So without having to type it out or get hash code or any of that junk, we just have referential equality. So the next section, type providers, is probably going to thing that's going to make you say like, ooh, F-sharp's the best. F-sharps are types for free. And what I mean by that is that, let me see. If I'm going to do some magic behind the curtains here for just a second. So what I just did, actually I'll explain the magic behind the curtains, is I just loaded up all the NuGet packages that this is referencing, and I threw them into this F-sharp interactive thing so I can later utilize them. So I'm just basically loading all my NuGet packages into here. And given that, I can open all the namespaces I need, which just takes a second. And what I'm going to do is I'm going to create some types by just giving F-sharp some strings. And you can do this with a lot of things, more than just JSON or XML. So the first thing we're going to look at is a JSON type provider. And what JSON type provider is going to do is it's going to look at all the internals and basically create types from it. So if I run this, blah, 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 and if I create this other type with some more complex JSON, which has a number of different elements inside of it, then what I can do is I can take that more complex JSON text, which is this guy, and I can say, give me the sample, so get me this stuff, get me the actual data that I need for this, and iterate through it. So think about that for a minute. F-sharp, F-sharp's not iterating, but compiling this linearly, or evaluating or whatnot. So F-sharp's going down this line of code, and it's saying, OK, I'm going to read this, I'm going to create this type, and then just on the basically the next line of code, it's going to grab the internals with the correct types, and I have dot IntelliSense or whatever on all the internals here. So I have the age and the name and all that stuff from doing nothing. That's not even anything compared to what we'll see in a minute. Just wait, there's more. So it's right here. I can, I created those types, and I'm going to go and I'm going to execute this interactive. And it looked at all those internals, and it said, OK, John is 94, and Tomas is also in the list. So it figured out, A, that this age is an int. It figured out that this name is a person, and it dealt with the fact that this has a name, but it has no age. And it created a type, basically like a record type with just a name and an age. And it generated it. You can kind of think of it as being like some code gen, but it's not really. And then it utilized it just a second later. So that's really cool. But what if we could do that with SQL? What if Stachu had a database on a system called FooDB, and he had 2 tables in it with no data? Well, I'll tell you what. Then we can create a type provider for that. So what we can do here is I can execute this line here, and that's going to, within a split second, it's going to call my database, ask it what tables exist, what columns exist in those tables, and it's going to create all the types necessary on the fly. And then a second later, I'm going to get the data context for that situation. And I am going to say, whenever you execute a query, you should console log it, because we want to see your nice little SQL queries. I'm going to create a type here that we're going to use in a second. Not much. And then I'm going to query my database. So I can use this syntax here, which is basically like LINQ in C#, but better, because it's using monads. It's not really, but whatever. So we're going to query our database in a LINQ-like way. And basically what I'm going to do here is I'm going to do just a join from my orders table to my order details table on order detail order ID equals order detail dot order ID. Just normal SQL query. I'm going to take some different information for that. I'm going to iterate through it, and I'm going to print out some information. The tables are empty, so you won't see any actual numbers, but you will see a SQL query when I execute this interactive. So that just executed that SQL. I didn't have to do any code first or database first code generation or any of that. I just told it, here's my connection string, and it said, here's your types, which, I mean, that's awesome. It's really great for like ETL. Just the other day, I upgraded a system from ASP.NET 4 using some like old MySQL database or something, and I had one connection string pointing to a MySQL database, and I said, okay, I want to take that data, and I want to copy it all to a SQL Server database with a slightly different syntax, not syntax, but what's the word I'm looking for? Schema. Yep. So I just basically got 2 of these little type providers, and I said, okay, here's a connection string to my SQL database on production. Here's something on my SQL Server pointing to my local that I want to copy to, and I gave it the connection strings, and I basically just said copy with like 20 lines of code without having to create types or any of that nonsense. Or export to CSV, because who wants to do that? So that's really cool. Type providers are awesome. There are type providers for a lot of things. We have type providers for XML. Yeah.
Did you read that definition on 33?
The definition of, I cannot see 33. Let me see. Oh, the only reason I use that is because this select is projecting to this type. Anonymous types do not exist as far as I'm aware in F#, which is a pain point for me a lot. So that's all I'm using it for. But yeah, we have type providers for a lot of things. We have type providers for JSON, and that works if you're pointing to like a remote service. Like I queried the GitHub API via type provider. So I just basically pointed a connection string to the type provider, or to the URL that the API exists on, and I said, okay, go grab all the functions that exist on the API and give them to me, and then I will query them however I need. And it figures out the types that it needs and everything. So that's pretty cool. And so it does JSON. It does XML. Not that anyone does XML, I'm just kidding. It does CSV, Excel. You can basically talk to anything, like OData. And if you want, you can actually write your own type providers. For example, if someone made a chess type provider in which he just starts typing on the computer, and like after he types in like F4 and he hits dot, it displays an IntelliSense of a chessboard, and like it shows you what moves are possible, which is kind of stupid, but it was just a fun. Basically, the idea is you can create anything with a type provider, as long as there's some data source that you have needs to access. So those are type providers. Events are okay, but actually I'll go through it. So I have the shortest WinForms app ever. I'm going to open 2 namespaces. I'm going to create a form. And I'm wiring up an event such that whenever I click on the thing, it should yell at me. So while I'm in Visual Studio, no F5, no nothing. I have this going. And events are cooler in F# because we have like events as like first-class citizens where I can basically use link in an observable kind of way to filter all the events that are happening on an object. So what I have here is I'm saying whenever I move my mouse, if the x coordinate of my mouse pointer is less than 20, then yell at me or tell me where my coordinates are. So I'm going to sneakily move my mouse over here, and when I start moving over here, it'll tell me all that. So that's really cool. I mean, WinForms app in, 12 lines of code or something? Not that we write WinForms apps now. But so did you have a question? I thought I saw a hand. Yep.
Did that seem to imply that you might not even need reactive extensions in F#?
I cannot answer it with like full confidence. So I'm not sure. Maybe this is using reactive extensions underneath.
No. It would have to open some other namespace.
Different namespace, maybe. But yeah, I don't know is the best answer. Or at least it's the only honest answer I can give. So simple test is boring. Let's go through an interesting test. We got like 5 minutes left, right? It's like 10:15. Cool. So what I'm going to do is I'm going to go to ReSharper, and I am going to tell it to run all my unit tests so I can show you some failing unit tests. And this is probably going to be the last thing, and then we'll call it a day. And let's hope that F# can find my unit tests. Oh, wait, I think it's just hidden. Where is... All right, for some reason, it's not finding my unit test. So that is out.
Have you compiled the project?
I feel like the unit test runner would do that, but maybe not. Bum, bum, bum.
Almost anything that goes up against F#. Let's compile first.
Yeah. Well, F# evaluates like along the way. One fun fact about F# is the fact that all these files are actually evaluated in order. So you might notice that in this alphabet, E comes after T, but it's not really like that. It's not sorting by alphabetation, if that's a word. Instead, I'm manually sorting these. So this entire file is going to be evaluated before the next file is evaluated. And you might initially think of that as really painful, but it's actually really nice for a number of reasons. The main reason is that if I have a bug on like here, I know that like if I have a compilation error here, I only have to look upward to try to find the bug. I know it's not going to be below. And also helps for complexity. It kind of forces you to modularize your code. Yeah. All right, I think I gave that enough time to do this. So if I run these and cross my fingers, then nothing will happen. That's fine. So I think that's it. Any questions at this point? Cool. Well, thank you guys for coming. I hope you gained a little bit of knowledge of the Rubik's Cube. Probably more than you anticipated. I hope you guys enjoyed the F# stuff. And if you guys have any questions afterward or you want to see more of the code that I kind of glossed over, let me know. But thank you guys so much.